All right, the next thing that I wanted to talk about was this idea of Cepheid variables. Cepheid variables are really, really important to us when we're trying to figure things out about distances and other things. Remember, we've been talking about the idea that we're trying to use our knowledge of physics to be able to learn things about the universe around us. Now, the first Cepheid variable, delta Cepheid, was discovered in 1784. Okay, it actually changed its brightness. Now, this was something that maybe wasn't recognized by the naked eye right away, but it was found that there was this star that was getting brighter and dimmer, and it wasn't over a galactic time scale. Usually we talk about stars taking millions and millions of years to get older and younger, to get born, to die, all these other things. So normally it would be millions of years. For some reason, in 1784, they found this star that was taking a matter of days, right? Took 5.4 days to go from this very brightness down to dimness, and then it would get brighter again, okay? And it actually repeated this over and over and over again, okay? Now, over the next 100 years or so, more of these Cepheid variables were discovered. And as they discovered these, they found out that there was a linear relationship between the luminosity and the period. This is what they found. They found that as the period increased, that meant that it was actually a more luminous star. Now, they did find out that there were two different lines going on here, okay, which was an interesting discovery because initially they just had a bunch of points and they were trying to draw one line down the middle. But eventually they found that there were actually two different things going on. Okay, and we won't go into the details of most of that. You just need to recognize that there's a linear relationship between luminosity and period. Now, of course, this was done using all the other things that we've talked about, using apparent brightness, using parallax. All these other things were used to help us figure out what the luminosity of those stars were so that we could then compare luminosity and period. Now that we have this information, right, we don't have to prove it anymore. Okay, now that we have this information that the luminosity and the period have this linear relationship, now anytime we find a variable star, we can measure its period. And if we measure its period, we can use the period and our other knowledge, whether it's a type 1 or type 2, to be able to determine what its luminosity is. Now that's important because if I can find its luminosity and I know its apparent brightness is, I now know its distance. Now because of this, these are often called standard candles. Okay? They are used as a standard to help us find distances throughout the universe. Okay, now this is really, really cool because now I don't need to measure all those other pieces of information. All I need to do is find a Cepheid that's changing its period. I use the period, use the period to find the luminosity, use the luminosity and the apparent brightness to find the distance. And that's why it's called a standard candle, because it's used to help us find distances of stars throughout the universe. Now, again, we talked about the idea of globular clusters and open cluster stars that are close together. So if I can find the distance to a Cepheid variable within that cluster, I have a pretty good idea of how far that whole cluster is from me. So this is really kind of neat in how we can use these Cepheid variables. This is a very common question, by the way. Make sure that you know what Cepheid variables are and what they do, and they're important. Okay, now I do want to talk about actually what's going on here. Okay, what is going on inside the Cepheid star, inside the Cepheid variable? Okay, we're not going to go into a lot of the details, but the general process we want to understand. Okay, so what's going on here? We're going to start here at 6 and move into 1. Okay, so what's going to happen is the star, for some reason, loses its equilibrium. Okay, when it loses its equilibrium, starts to cool off, gravity starts to pull the star inwards, right? If there's not anything, we call it radiation pressure, is usually that heat, that energy is what's pushing the star out so it doesn't collapse in on itself. If that's not there, if the star cools off, it loses equilibrium, then the star will start to collapse on itself, all right? Now, as it collapses, it becomes more dense. As it becomes more dense, the fusion inside continues to happen. It continues to burn. But as it becomes more dense, the energy that's being created inside can't get out, okay? So as that energy can't get out, it heats up. The pressure builds, and then it pushes that dense surface back out again, okay? Now, once that surface gets back out again, much of that energy is released out into the universe. Now, once that energy escapes, it's now less dense, it cools off, and therefore we then repeat the process again. All right, so see if you can walk yourself through that process. Maybe pause the video, go back, rewind the video, see if you can talk yourself through that process again. If you need to, just rewind it and listen to me go through it again, all right? But it's important to understand why that's happening. Again, that's a question that's asked. Okay, well, we understand why Cepheid variables are important, but what is the process that's going through there? All right, so go ahead, give that a try, and then move on to the next slide. All right, so this is a type of question that may be asked about Cepheid variables. All right, if you would, when I ask you to pause it, go ahead and pause the video, take a couple of minutes to work through this question, and then unpause it, and I'll go, kazam, here's the answers. All right, so go ahead, pause the video. Shazam, there we go. All right, so here we go, let's look at this. We've got the part A, luminosity is the total power output of a star. The apparent brightness is the intensity or power over area of the light from a star at a specific observed distance. You got formulas for those, you can describe those. State the mechanism for the variation in luminosity of the Cepheid variable. Please rewind the video and you can look at that. That was just the section right before this. The slide right before where I talked through the process. That's the mechanism that it goes through. Okay, so you can check that out. Okay, next is here, assuming the surface temperature of the star stays constant, deduce whether the star has a larger radius after 2 days or after 6 days. Well, we can see that the apparent brightness is going down from A to B. If the apparent brightness is going down, that means the luminosity is going down because of the relationship between luminosity and apparent brightness, which I did write down there. So if the luminosity is going down and temperature is going the same, it must mean that the surface area is going down. If the surface area is going down, because surface area is 4 pi r squared, it must mean that the radius is going down. So that's the answer to that question. After 6 days, the radius is smaller. That's why it's less luminous or less apparent bright at that point. All right, the next question, explain the importance of Cepheid variables. Again, please rewind the video. The basic idea, of course, is that there's a linear relationship between period and luminosity. So with the period, I can calculate its luminosity. Given the luminosity and the apparent brightness, which I can measure because that's just how bright does it look, I can then calculate using this formula down here, the distance. It is important that you recognize and mention that it's a linear relationship between the temperature and the luminosity. All right. The next thing is part I. Okay, I'll let you do the calculation here, but you should use this formula. We're given the luminosity in the question. We have the apparent brightness up here on the y-axis, so we are using the apparent brightness there. So we have the apparent brightness, we have the luminosity. That should allow us then to solve for the distance. This is the answer you should get. Check it, make sure that you can get it. All right, that's just a matter of plugging it into a calculator and either using InSolve or actually doing a little bit of algebra there to get the answer. Okay, the last question is Cepheids are sometimes referred to as standard candles. Explain what is meant by this. But again, the same idea that because we can use it to determine distance, then anything that's in its immediate vicinity, we know the distance more or less of those things as well. So it's a standard for measuring things around it or measuring other things in the universe or the galaxy. All right, so there you go. That's good enough for that example question. Just one or two more things before we wrap up this video. Now we have a way of dealing with temperature. We can also measure luminosity. So we've got a whole bunch of information here. What happens when we put temperature and luminosity together? Okay, this is what we get when we put temperature and luminosity together. You see we've got temperature down here on the x-axis. You've got luminosity over here on the y-axis. Now, much of the time what you'll see is on the y-axis it will compare the luminosity of the star that we're looking at to the luminosity of this circle thing. That circle thing is the sun. So it's just how does the luminosity of that star compare to the luminosity of our sun. That is why the sun is essentially right on that 10 to the 0. 10 to the 0 is 1, so that would be, it is the luminosity of our sun. All right, so the sun should be right on that 10 to the 0, which it is in both of our drawings. These are just two different things giving us an idea. The one over here on the right, yes, is much more colorful. It gives us a little bit more on the idea of size. The one over here on the left just gives us some specific dots. Now, what you'll see is that most of the stars lie along this kind of central curve. Now, it is a curve. It's not a straight line, though it may seem a straight line. These are what we call the main sequence. Most stars, this is the general life of those stars. Okay? We'll talk about these cool, bright stars later, and we'll also talk about these ones that are either very hot and dim or starting to become more cool and dim. We'll look at those. When we put all these things together, these are called an HR diagram. All right? Hertzsprung-Russell. And I'm not going to spell that out. You can look it up in your book. Okay, but that's all this is. It's an HR diagram. This is going to be really, really important as we start to talk a little bit more about doing some interpretations. Okay, most of the stars, like I say, about 90% of all stars are on that main sequence there. Most of the time they're fusing hydrogen and helium, possibly a little bit of carbon. Okay, how is it possible that a cool star, think about these cool stars here, how is it possible that these cool stars can be so bright? How could that happen? Well, remember that luminosity depends on two things, right? Luminosity depends on area and temperature, okay? So yes, the temperature is low, but that must mean that they must be very, very large, and that's where we get into this idea of our giants and our supergiants. If they're really big, they can still be very, very luminous, even at low temperatures. All right? So, we can see those types of things by looking at black body curves and things like that to get temperatures. So a lot of this we'll be talking about shortly, but I wanted to introduce you to this idea of HR diagrams because you are going to be seeing them. Now, one last thing that I do want to share is this is one final relationship that's used quite often. Okay? Generally speaking, for a star to be stable, it needs to be in hydrostatic equilibrium. Okay, that means that the pressure of gravity pulling in, so here's my star, I've got gravity that's trying to pull those gases in, but then I've got fusion happening on the inside, and that fusion is creating what we call a radiation pressure out. Radiation pressure pushing out, and we've got gravity pushing in. Now, if it's in hydrostatic equilibrium, then those two things balance each other, right? Now, something with a higher mass means that I've got to have higher gravity, okay? So if the mass is bigger, then the gravitational force is going to be bigger, all right? Now, if it has a higher gravitational force, then that means that the radiation pressure needs to be bigger. But why would there be more radiation pressure? Well, there's only going to be more radiation pressure if it's creating more energy, meaning that there's a higher luminosity and therefore a higher temperature. Okay, now what this means is that there's going to be a relationship between mass and temperature. A higher mass, because of higher gravity, means that there has to be a higher temperature in order for this balance to take place. Now, this is the relationship. You don't need to know the exact equation, but if something has a particular mass, it will have a certain proportionality to the luminosity. Okay? Now, of course, a higher temperature means that you're burning things off a lot faster. Now, this means actually that something that has a higher luminosity, a higher mass, is actually going to have a shorter lifespan. Okay? Because of the higher temperature needed, it's going to be burning off that mass, causing fusion much, much, much faster than something with a smaller mass. So a star that's, let's say, a star that's 10 times the mass of the sun, right? That's the symbol for the sun we talked about before. So one that's 10 times the mass of our sun will be about 3,000 times brighter. But in order to be 3,000 times brighter, it's going to be burning off that mass. And so therefore, its lifespan will be about 1,000 times shorter. All right, so these are some ideas that are going to come up as you're starting to work through some more problems. Pay attention. Remember that this is one of those relationships. This is in your formula packet, that the luminosity is proportional to mass to the 3.5 power. And so you can create ratios with this, much like we did with the luminosity and apparent brightness and all those things that we did before. All right, that's going to be enough for today. All right, or sorry, for this video. Go ahead and move on, and you can watch the next one after you do, go do some problems, and you can move on.